This problem's a little bit harder than the previous problems we did because in the previous problems, we were told what kind of equation we needed to use, whether it be the mc delta t change in temperature equation or the ml change in phase equation. Now, in this case, we really don't know, and that's what they're asking. They're asking not only the final temperature of the mixture, but also which phase it's going to be in. So we don't readily know if we need to use mc delta t or ml or the combination of the two. So the first thing we need to figure out is, well, what's the phase it's going to be in and then work from there. What we're given is the mass of the ice, mass of the tea, the initial temperature of the ice, and the initial temperature of the tea. So we're basically making iced tea. Now, in thermodynamic equilibrium, they're all going to be one particular phase and one particular temperature. We need to figure out what both of those are. So the first thing is to find out, will the mixture be a solid or a liquid? In order to find that out, we're going to do this first. We're going to look at how much heat does the tea need to give off in order to turn into a solid. So what we're going to do is we're going to look at the mc delta t of the tea and the final temperature. This means that right when the tea starts to change phase, we're going to make that 0 minus T naught of the T. So that's how much energy right here it takes for the T to reach a point when it starts to become solid. We're going to go ahead and just label this. This is how much energy lost to bring T to transformation point. All right. And now we're going to also compare that with the amount of energy it takes ice in order to bring it to the point in which it also transforms. Okay. And to be honest, we can also look at how much energy it takes to bring T to a point of transformation and to transform it into a solid. And we can compare it with the amount of energy it takes ice to bring it to the point of transformation and to transform it. But what we're going to do instead is we're just going to bring it to the transformation point, and we're going to assume that that one of the two is never even going to get there. So that means all we're going to do is we're going to compare the energy it takes or loses to bring one or the other substance to the transformation point without actually transforming. Again, this is with the assumption that they will never get to that point anyways when they mix. Of course, if they do get to the point and they're halfway through the transformation, then that's going to be more of a problem of what percentage is going to be liquid versus solid. Okay, so all we're going to do is we're going to bring the ice to the transformation point of 0 degrees Celsius, subtracted with the initial temperature of the ice. And again, this is how much energy gained to bring ice to transformation point. Excuse my chicken scratches. Okay, when we do the calculation, we see that this, and that is by plugging in 3 kilograms here, 4186 joules per kilogram Kelvin here, and plugging in 20 degrees Celsius here, we get a whopping 250,000 joules. And that's how much energy that has to be lost by T in order to at least get it to that transformation point and to start transforming. Now let's see how much energy must be gained by ice in order to get it into the transformation point and to at least start to transform. It ends up being, by plugging in all the numbers given up here in the knowns table, it ends up being 177,000 joules. So what we're seeing here is that it takes more energy lost from the T to transform it than does it take gained by the ice to bring it to the transformation point as well. So if that's the case, that means that it is more likely that this whole contraption will be in liquid phase. Since it takes more effort to turn T into a solid than it does to turn the solid into the liquid, we know it will probably most likely be in liquid. Actually, we know for absolute certainty it will be liquid. It takes more effort to get liquid to solid than solid to liquid. Therefore, it will remain a liquid. So the answer to this is it will stay in liquid phase. And you answered that part of the question. Now, this is great because you actually need this to find the second part of the problem, what the equilibrium temperature is. Now we're going to do what we did in the previous two problems that I worked with you on. And we're going to look at Q lost by T equaling to positive Q gained by ice. But this time, since we know that ice is the one that's doing all the transforming and T just stays where it's at and just changes its temperature, we are educated on the equations we need to use. So for T, all it does is get a little cooler, right? So we're going to say M negative M of T, C of T, change in temperature of T. And then we're done for the left-hand side. There's no phase transformation, so no ML needed. Now for ice, since ice starts off at below freezing point, it has to go above to the freezing point, has to transform, and then it has to raise above the freezing point into the liquid phase. So we're going to have three terms for ice. Again, that's going to be the ice getting to the freezing point from below freezing. Then the ice transforming. And this is L sub fusion of H2O. So that's just going to be L of ice. But I just make it generic by saying the fusion latent heat for H2O. And we're going to have to put in a term for the water version of that ice. Sounds weird to say that. To go to that final temperature from the freezing point. So to the freezing point, transform, and then to the final temperature from there on out. Seems kind of a pickle. But again, we have TF that we need to find out. So we need to figure out how to isolate TF. Okay, now let's go ahead and do that with two steps. The first step is I'm going to break this all down and try to get TFs all on one side. But let's go ahead and first do a breakdown. And now let's go ahead and isolate TF by just bringing all TFs on one side, putting everything else on the other side, and then trying to split up the TF with the rest of the parameters here. And where we're going to get is TF equaling to the following. Now, what we're going to do is plug in all the numbers. You're only given a few, but a lot of it could be found online. So for MT, we have 3 kilograms. For the latent heat, I'm sorry, for the specific heat of T, that's the same as that of water. It's going to be 4,186 joules per kilogram Kelvin. For the initial temperature of the tea, we got 20 degrees Celsius. And we're going to keep this in Celsius so we can get the final temperature in Celsius. Mass of the ice is a half kilogram. Specific heat of ice is going to be 2090 joules per kilogram Kelvin. Again, this is found online. The initial temperature of ice is going to be negative 10 degrees Celsius. Mass of ice already given. The latent heat of fusion for H2O is 333,000 joules per kilogram. 333,000 joules per kilogram. That's found online. Mass of the tea, heat capacity of the tea already given. Mass of the water is going to be the same as the mass of the ice. So that's still going to be half a kilogram. And then the heat capacity of water is the same as the heat capacity of tea. And that's going to be 4,186 joules per kilogram Kelvin. So putting all this together, and don't mind the estimates because there's going to be a little bit of discrepancy. It's going to be roughly 5 degrees Celsius. And that is going to be the final temperature of the iced tea after all the mixing is done. And of course, because it's going to be in liquid phase, so this makes sense. It has to be above 0. I just did a mic drop there. All right.